So, hello everyone again. This is lecture 6 part 3 of current electricity. Today we will go on with the further discussions of examples of Wheatstone bridge only. What is Wheatstone bridge? So, in the final example I explained you the balanced condition of Wheatstone bridge. We will move on with a little bit more detailing of that and then we can move on with the further discussions. So, I am Sameer Lavankar. Let us begin our discussion. Okay, so right now we are on the 14th point, that is the Wheatstone bridge. In the previous lecture we completed the Kirchhoff's rules and its examples, and then after the completion of Wheatstone bridge we will move on with two more applications, that is meter bridge and potentiometer, and that will be the end of current electricity. So, Wheatstone bridge. So, finally in the last lecture what we got was that for a balanced condition, what is a balanced condition? For the balanced condition to occur, first of all let me write. So, for balanced condition to occur, the current passing through the galvanometer should be equal to 0. First of all, this is a definition of balanced condition, and for this balanced condition to occur, the condition which is required for the 4 resistors should be that the resistors in the left hand direction, that is R2 by R1 should be equal to R4 by R3. So, this is the condition. Okay, let us move on. So, this last equation relating the 4 resistors is called as the balance condition for the galvanometer to give 0 or null deflection. So, if we try to reverse this complete concept, we can just say that if the resistors R2 by R1 is equal to R4 by R3, then we can say that the balance condition has been achieved, and in this complete concept, in this complete series of resistors or in this complete group of resistors, we will find out that the current passing through the galvanometer will be equal to 0. Okay. So, this thing has been explained. Next is that the Wheatstone bridge, and its balance condition provides a practical method for determination of an unknown resistance. So, what does it try to say is, so we have the equation for balance condition is R2 by R1 is equal to R4 by R3. So, let us suppose that this R4 is unknown. So, how can we find out the value of R4? R4 is nothing but R3 multiplied by R2 by R1. So, the Wheatstone bridge and its balance condition provides a practical method for determination of an unknown resistance. Let us suppose we have an unknown resistance which we insert in the 4th arm. What is the 4th arm here? This is the 4th arm being talked about, this is the 4th arm. R4 is thus not known. So, R4 is thus not known. Keeping known resistances R1 and R2 in the first and second arm of the bridge. So, all these resistance are being known. Means R1 and R2 is known and R3 is a variable. So, we just try to change the variable R3 such that we get our balanced condition. Okay. So, keeping known resistances R1 and R2 in the first and second arm of the bridge, we go on varying R3 till the galvanometer shows a null deflection. Quite evident, this is the complete procedure which has been explained here. The bridge then is balanced, and from the balance condition the value of the unknown resistance R4 is given by R4 is equal to R3 into R2 by R1. So, this is the equation being used here. A practical device using this principle is called as the meter bridge. So, how does a meter bridge use this complete application? I will explain to you. It will be discussed in the next section, right. So, nothing to explain it more, just to iterate again what is happening here. We know the value of R2 and R1. Let us suppose the R2 and R1 value is, let us say 5 ohms, and let us say this is also 5 ohms. So, as we know this value, so we need to find out the value of R4. Let us suppose the value of R4 is, let us say 10. Then what do we do is, for now we do not know the value of R4. So, therefore, R4 will be nothing but R3 into 5 by 5. Hence, we will start varying R3. We go with 1, then 2, then 3, then 4, then 5, then 6, then 7, then 8, then 9. Till these all points the value of galvanometer was being showing. There was a deflection in the galvanometer's needle. At 10 the galvanometer needle won't deflect, and hence finally we got the balance condition. And hence what we found is that as R3 is equal to 10, and using this equation we can find that R4 is also equal to 10. So, finally, we got the value of the resistance of the unknown resistor. Okay, let us move on with the further discussions now. So, now let us example of this Wheatstone bridge only. Please look over here carefully now. So, the 4 arms of a Wheatstone bridge have the following resistances. So, what are these resistances? So, AB is given to you as 100 ohms, BC, where is BC? BC is given you as 10 ohms, CD is given to you as 5 ohms, and DA is given to you as 60 ohms. Okay. A galvanometer of 15 ohms resistors. Please make sure here galvanometer also has a resistance. There will be a resistance in this portion also. So, a galvanometer of 15 ohm resistance connected across BD, quite evident. Now, calculate the current through the galvanometer when a potential difference of 10 volts is maintained across AC. So, this question is not of a balanced condition, this question is of a Wheatstone bridge. So, calculate the current through the galvanometer when a potential difference of 10 volts is maintained across AC. Okay. So, quite evident, just a simple use of junction rule and loop rule will give you the results. So, let us move on. So, consider, let us see the solution now. Considering the mesh BADB, so BADB, so this is a loop first of all. Let us go on with the what is the loop saying here. So, as the direction for the 100 ohm current is opposite, so it will be plus I1, so IR, so it is I1 into 100. For 60 it is in same direction, therefore it will be equal to minus I2 into 60, and in this it will be again in the opposite direction, it will be plus Ig into 15, I guess, yes. So, this is the first equation here, as you can see, minus 100 I1 plus 15 Ig minus 16 I2 equal to 0. Next is BCDB. So, BCDB. So, hence this is the loop here being talked about. Let us move on with this discussion also. So, it will be equal to nothing but minus 10 into I1 minus Ig BCDB. Okay. Next is plus I2 into I2, sorry, plus I2 plus Ig into 5, and next is again nothing but plus, why plus? Because we are going in opposite direction of Ig into 15 equal to 0, and hence this is the equation being talked about here. It is just in the negative sense. So, if you just change the condition, it is minus here, plus here and plus here. As you can see, these both equations are same now. Okay, let us move on. So, we know we have now two equations and we have three unknowns. So, we need one more equation for the complete analysis to take place. The third condition, the third mesh is consider the mesh is ADCEA. So, let us look over here, ADCEA. So, this is the loop being talked about here. This is the loop. So, let us move on with this loop also. So, what is happening here? So, first of all we will go on with I2. So, for I2 it is minus 60 into I2 minus I2 plus Ig into 5 plus 10 is equal to 0. So, it is nothing but if I put these two portions on the left, opposite direction, we will get 10 is equal to 60 I2 plus Ig into 5. Hence, three equations and three unknowns are nothing but I1, I2, Ig. So, three equations, three unknowns, and finally, we can find out the value of different currents passing through the different things. As the questions are about the Ig value, so by some different mathematical operations, you can directly find out the value of Ig. Okay, so after mathematical formulations, we will get that I2 is equal to 31.5 Ig. Substituting the value of I2 in one of the above equations, we get Ig is equal to 4.87 milliamperes. So, finally, it is just mathematical formulation. I am leaving the mathematical formulation for you. After mathematical formulation, you can find out the value of Ig is equal to 4.87 milliamperes. Okay. So, the next example is meter bridge. Meter bridge is a peculiar example of balanced condition of Wheatstone bridge. Let us move on to and look over what is this meter bridge. Okay. So, the meter bridge is shown in the figure. So, this is an example of a meter bridge here. As the name suggests, meter. So, meter here means scale of a meter length, that is 1 meter is nothing but 100 centimeter is being utilized, and that is being put to use for the balance condition to take place. Okay, so, the meter bridge shown in the figure, it consists of a wire of length 1 meter. So, this is that wire, this is that wire, this is that wire of 1 meter length, and of uniform cross sectional area. Please, this is very important, a uniform cross sectional area should happen. Why? Because so that the resistance at every point should be same. Why? Because we know that the resistance is equal to rho L by A. If the area is changed, the resistance will also change. Okay. So it consists of a wire of length 1 meter and of uniform cross sectional area stretched, taut and clamped. What does taut means? Taut means that the complete tension has been achieved. There is no dilation, there is no undulations in the wire. It's completely strengthened apart. Okay. So stretched, taut and clamped between two thick metallic strips bent at right angles. So these are the metallic strips we talked about. So it is clamped between these two thick metallic strips. Okay. Bend at right angles as shown. Okay, so this thing has also been explained. Now next is the metallic strip has two gaps across which resistors can be connected. So these are the gaps being talked about here through which a resistor can be connected. Okay, fine. So this thing has also been explained. Next is the end points where the wire is clamped are connected to a cell through a key. So now the end points. What are these end points? End points where the wire is clamped are connected to a cell through a key. So this thing has been explained here, and this is the key being tagged here. Okay, so this thing has also been explained. Next is one end of a galvanometer is connected to a metallic strip midway between the two gaps. One end of the galvanometer, so this is the end, and is connected to the metallic strip midway between the two gaps. So these are the two gaps, and this is the metallic strip being talked about here. So quite evident. So it is connected to the metallic strip midway of the two gaps. So this thing has also been explained here. Next is the other end of the galvanometer is connected to a jockey. Now what a jockey, you might ask. So this is an example of a jockey. So this is a jockey. So this is explained at the other end of the galvanometer, and we try to put it on the metal, that 1 meter metal. Okay. So this thing has also been explained now. The jockey is essentially a metallic rod whose one end has a knife edge. So this is the knife edge which can slide over the wire to make electrical connection. Very evident, quite evident. Now R is an unknown resistance whose value we want to determine. So this is the value which we don't know. It is connected across one of the gaps, quite evident. Across the other gap we connect a standard known resistance S. So this value is known. And this value is unknown. Okay. Across the other gap we connect a standard known resistance S. So this thing is explained. Let's move on. So I explained you the complete diagram of what is happening here in the meter bridge. The jockey is connected to some point D on the wire. So let us suppose let us suppose this is a jockey and this is that metal wire. I am putting the metal wire at this portion here like this. Or let us suppose I am putting let's say this is the complete metal wire and I am putting my jockey at this portion here. Let's say this is the point D. Okay, so the jockey is connected to some point D on the wire at distance L centimeters from the end A. So I am assuming that this is the L centimeters from end A. Quite evident, if this is L centimeters, then this is nothing but 100 minus L centimeters. Why? Because this is a meter bridge. It is a meter bridge. The wire is 100 centimeters in length. Therefore, the L it is 100 centimeters. Therefore, it will be L1 centimeters, and it will be equal to 100 minus L1 centimeters. Okay. So the jockey is connected to some point capital D on the wire at distance L centimeters from end A. The jockey can be moved along the wire. So as I explained, the jockey can be moved along the wire like this. Why? As it has a knife edge. As it has a knife edge. Okay, which can slide over the complete metal wire. The knife edge can slide over the complete metal wire. Okay. Next is the portion AD of the wire has a resistance R centimeter L. Quite evident, as you can see now. So now first of all let me explain what is R centimeter. Yes, so it is written here directly. R centimeter is the resistance of the wire per unit centimeter. So if it is resistance per unit centimeter, the complete resistance which is denoted by this portion will be nothing but RCM multiplied by L1. Similarly, the resistance portion by this portion will be nothing but RCM multiplied by 100 minus L1. So if you look very carefully, these can be the 4 resistors being talked about here. So if I explain it more in peculiar sense, let us say this A and C be the battery arm, let us say this is the resistor R, let us say this is the point A, this is the point C, this is the resistor R C M into L, 1 and this is the resistor RCM into 100 minus L1. This is the unknown resistor R, this is the known resistor S. So, now using these values we can directly find out the value of resistor R, because we just need to find out that point at which we will try to vary. We will try to vary this, and at that point at which the galvanometer will show the value of 0, and that value of 0 we will find out the value of resistance using the mathematical formulation. What will be the mathematical formulation? Very easy, I will try to explain, but for now you can directly see that this is nothing but an example of a balanced condition of a Wheatstone bridge. Okay, let us move on. So, the portion AD of the wire has a resistance R centimeter into L, where R centimeter is the resistance of the wire per unit centimeter. The portion DC of the wire similarly has a resistance R centimeter into 100 minus L. I explained you this also. The 4 arms AB, BC, DA and CD. So, AB, BC, DA and CD with resistances R, S, R centimeter into L and R centimeter into 100 minus L obviously forms a Wheatstone bridge with AC as the battery arm, फिर AC as the battery arm and BD as the galvanometer arm, very evident. Next let us move on. If the jockey is moved along the wire, then there will be one position where the galvanometer will show no current, quite evident. So, I will try to change the distance and I will find a point at which the galvanometer shows no deflection. Okay. So, let the distance of the jockey from the end A at the balance point be L is equal to L1, that is the point at which the galvanometer shows no deflection. The 4 resistances of the bridge at the balance point are R, S, R centimeter into L1 and R centimeter into 100 minus L1. So, for the balance condition to achieve, it will be nothing but R1 upon RCM into L1 equal to S upon RCM into 100 minus L1. We can also write this equation as R by S is equal to RCM into L1 upon RCM into 100 minus L1. So, this is the same equation which is written here. So, now just making it more easy, RCM gets cancelled, therefore, the unknown resistor R is nothing but S multiplied by L1 upon 100 minus L1. There is even no use of RCM also here. So, finally, what we can infer from this equation here, that if we know the value of capital S, that is the known resistance S, and we try to vary the meter bridge, we try to vary the jockey, we will find a point at which the value of L1 by 100 minus L1 will be such that we will find out the multiplication of S with this equal to R, and hence we will find out the value of unknown resistor R from this method here. Okay. So, next step, by choosing the various values of S, we would get various values of I1 and calculate R each time, quite evident. An error in measurement of I1 would naturally result in an error in R, very easy, because if we got the value different for L1 or 100 minus L1, L1 will also change, 100 minus L1 will also change. Due to these two portions, the value of ratio will change, and due to this ratio also the value of resistance will change. So, an error in measurement of L1 would naturally result in an error in R. It can be shown that the percentage error in R can be minimized by adjusting the balance point near the middle of the bridge, that is when L1 is close to 50 centimeters, this requires suitable choice of S. So, what does this last line says, I will try to explain, and that will be the end of this lecture here. So, this line try to say is that we should at least know the range of that resistor capital R. Let us suppose we take the resistor to be, let us say 100 ohms, it is around the range of 100 ohms. So, we should take the value of S also should be equal to 100 ohms only, so that we will get the value of L1, and L1 should be approximately equal to 50, and hence there will be no error. Let us suppose we take the value of S as 100 ohms and the resistance range is unknown as 10 to the power 4 ohms, let us suppose, then the value of L1 will come very small or very large, and that may give error results. That is why it is completely said that if to get good results, the L1 should be approximately equal to 50 centimeters only. So, this is the end of the meter bridge. So, finally, what we got is the equation, that is R is equal to S into L1 upon 100 minus L1. So, let me stop it here only. So, the course progress for you, we start with the introduction of this chapter. Electric current is done, that is the mathematical formulation, then electric current in conductors followed by Ohm's law, drift of electrons and origin of resistivity, limitations of Ohm's law, resistivity of various materials, temperature dependence of resistivity, electrical energy and power energy, found out the value of V into I, that is equal to I square R is equal to V square by R. Then combination of resistors series and parallel is done. Cells, EMF and internal resistance are new different formulation of what is EMF. EMF is nothing but the potential difference, which is also called as the electromotive force. Please make sure electromotive force is not a force, it is a potential difference. The next is cells in series and parallel. Then the Kirchhoff rules were explained in the starting of this part only, in this lecture 6 part 1. And finally we are at Wheatstone bridge is done, and finally today we start with the meter bridge. After meter bridge is done, there will be an example I guess, and after that potentiometer will be explained, and after potentiometer your complete current electricity chapter is done. So let me stop it here only. Thank you.